this is gonna be a proportion distribution, right? Because you have, what is the probability of a random sampling?
So this is sampling distribution,
Okay.
right? Where we look at a full population and then we can base our samples and the means off that population. So our sigma was 3,500. What's that 33,000?
That's your mean.
It's mu, right? So mu is 33,000. The 500 people that bought cars last week.
Population.
It's our population, right? So
Big N.
what was it?
Big N.
Big N.
Little N is 45.
Little n is 45. And then that 1,000 is just a piece that we will use when we're calculating our z-scores. So, we write down all the information that we know. Now what do we do?
You got a proof?
We need our proof, right? So what are your proofs for a z-score?
So
Little n's greater than
Little n's greater than what?
100. Is that it?
Okay, right, so one of them is if little n is greater than 100,
Greater than or equal to 30 with sigma given. And then bell shaped with sigma given, right?
yeah, like
Underlying.
told
Yeah,
that the underlying population
it's bell shaped with sigma.
is normally distributed and bell-shaped with sigma given. The vast majority of the time, 1 or 2 will be your proof. Right? Because she's going to want you to be able to truly prove to her that you can use a z-score or not. So, do any of these proofs check out? Which one? So on the exam, you would need to write down proof, n is greater than or equal to 30, sigma's given. All right, let's say we weren't working with means though. We were working with proportions. What is your proof for a proportion?
N times P is greater than or equal to 5.
and
And then
Times 1 minus b.
Right, both of those have to be true. All right, so this is step 1. We find our proof. What's step 2?
draw
Draw what?
your bell shape.
Okay, so we draw our bell curve. And what do we need to label on that bell curve?
So your sigma, your mu.
Right, all we need to do is show that our mean is 33,000. Now, what else do we need to do?
see if we can use the finite correction.
Okay.
formula.
So what's the rule for the finite correction factor?
And or sample n divided by population n is greater than or equal to 5. Greater than or equal to 5%?
Just greater than.
Oh,
So the greater than or equal to is our rules over here in our proofs. Our finite correction is if our sample is more than 5% of our population, we get to use the finite correction factor, right? So the finite correction factor is a bonus. What does it do for us?
Is it more accurate?
Yeah, so it will help really hone in on more truthful data for our population based off of a sample. So, do we get to use the finite correction factor in this problem?
no.
Right? Well,
Wait, what?
what's 45 over 500?
Maybe on that.
0.09?
Over. Sorry. Yes.
So we get to use the finite correction factor here, right? Alright, so now we know that we can use the finite correction factor. What do we use the finite correction factor while finding?
Standard area.
Standard error, right? So what's our formula for standard error?
Sigma over.
Divided by square root of sample size.
And then
The finite
the
correction.
finite correction factor, which is big N minus little n. And that's all under the square root there. So now we can start filling in based off of the information that we have written over here. 3,500 over the square root of 45 times square root of 500 minus 45 over 500 minus 1. So what is the standard error that you guys are getting?
$11,600. No. Maybe.
No. Yeah. 498.2155. So that's our standard error. What do we do next after finding that standard error?
Do we round up?
Well, so I think you want at least 3 decimals. It's either 3 or 4. So,
But since they're talking about car buyers?
well, we're talking about dollars.
Oh, okay.
Yeah. So what do we need to do next?
Find your z-score.
Find our z-scores, right? So we did all this work. So that way we could finally find our z-scores to figure out within $1,000 either way of our mean. So, we wanna find it for 32,000 and 34,000. Because we want that probability in the center. So what is our z-score formula now? Over our standard error. Right, so our x, let's say, is 34,000 minus our mu of 33,000 all over that 498 standard error that we just found. So the z-score for 34,000 is what?
$2.1.
2.01. So what would the z-score be for 32,000?
$2.1.
-2.01, right? So since they're equal distance away from the mean, you only need to find it for one of them. So we know that our z-scores are 2.01 and -2.01. We want to know the probability in between those two spots. What do we need to do?
Look at the table.
Take the difference between them, right? So we find that area and we find that area. So for -2.01, what was the area to the left? Okay. And what about for 2.01?
0.9778.
So if we take the difference of those, that will tell us the area between those two spots, and that is what?
The probability.
Oh, 556.
So, I'm sure she has reiterated this to your class, the importance of showing your work, right? The answer to that question is 0.9556. There was a lot of stuff though to get to that answer, right? So if you show all of this work, and then let's say you just mess up this final step, you're getting the majority of the points on this question. If you don't show this work though, she has no idea where you got your numbers from and can't give you any points. So make sure that you are writing down the formulas, writing down all the pieces, writing down your proof for the finite correction factor. Make sure you're writing all that stuff down so that way she can give you extra points. Even if you mess up here, she will find a way to still get you points. All right? So any questions over any of that? Any steps? No? Okay. So, let's talk about confidence intervals. What are the different pieces of a confidence interval?
Standard error,
Standard error,
margin of error,
margin of error.
mean,
What was that?
the mean.
The mean or the point estimate, right? So, those all make up a confidence interval. Before we get into this problem, let's just talk about some theory behind confidence intervals, right? So, how many margin of errors wide is a confidence interval?
2 intervals.
2, right? 2 margin of errors, plus and minus your margin of error. If you have higher confidence, a higher confidence level, does that make your interval wider or narrower?
Wider.
Wider, right? I'm 100% confident that's between 0 and 200 degrees outside. I'm 6% confident that's between 82 and 83 degrees, right? So as my confidence got smaller, I had to narrow my interval down. What about sample size? If we have a larger sample, what does that do to our interval? It makes it narrower, right? Because we have more data, so we can be more exact. What's alpha?
It's a significance level.
-1.
Confidence level,
Oh.
-1, right? But what's another term for alpha? Level of significance, right? So a 95% confidence level would have what as your level of significance?
5%.
5%, right? And then in the formula sheet, we always look up the Z or T score for alpha divided by 2. Why is that? It's either tail, right? Either tail of the bell curve. So we need to divide that alpha, divide our level of significance by 2. So let's take a look here at number 5. What pieces of information does number 5 give us?
So the standard deviation,
Okay, what kind of standard deviation?
population. So
Population.
So sigma,
So our sigma equals
4.
4 degrees. What else are we told? What was that?
The mean,
The mean?
I'll give it 85.
What kind of average is that? Is that population or sample mean?
It's me, X bar, right?
It's a sample mean, right? Because it tells us that a sample came back with that average. So X bar is 85. What's our sample size? $55, right? A sample of 55 days. And then we need to have a 95% confidence interval for the population mean temperature. So our alpha in this case is what?
0.05.
0.05. So alpha divided by 2 is 0.025. So we take a look at our formula sheet. We have 3 different formulas for a confidence interval. Right? We have 2 for a mean, and one for proportion. So which one should we choose?
But you gotta do a proof first.
So we do need to do a proof. We can also, knowing that we need to show a proof, we can also just take a look at what we're given, right? We're given sigma. So the formula that we're gonna need to use is the one with sigma in it, right? So that's some of the thought process that you might want to go through on the exam, right? Is figure out what you have and then look at a formula sheet and say, okay, what formula there uses this information? But if we want to show our proof, what is our proof to use a z-score? There we go. So we can start to write down our formula here. And then we get to the point of the finite correction factor. How can we tell if we can use the finite correction factor again?
That person.
But you can't because you don't have big N.
Right, so we would have to do little n over big N. We don't have big N, so we assume that the population is infinite, and there's no way that we can use that finite correction factor. So we just drop that off at the very end. So now we can just plug stuff in, right? So our X bar, that's 85, plus or minus our z-score, so we'll find our z-score, but we can fill in the rest of this. So 4 over the square root of 55. So now we just need to find this z-score. Need the z-score for alpha divided by 2. We know that alpha divided by 2 is 0.025. How do we find this z-score? So what are you guys looking for in your chart?
The area.
You're looking for 0.025, right? Inside the middle of the table. And the z-score that you find? 1.96. So you find it and it's negative 1.96, right? But since we're doing plus and minus, we can just drop off that negative part and just put 1.96. So probably the easiest way to do this is find your margin of error first, right? Find everything after the plus and minus. And when we do that, what do we find as our margin of error? Question. Okay. So that's our margin of error, right? Is that a confidence interval? Can we stop right there? What do we need to do?
Add or subtract.
Right, so we need to go 85 plus our margin of error and 85 minus. So when we subtract it, we get 83.9429. And when we add it, 86.0571. Now are we done? No. Something has to go between that,
Oh, mu.
okay? And
Greater than, less than.
right, so we need to show that our mu is going to be between that. So, what does this mean?
That you're 95% sure that'll be between those two numbers,
That what will be between those two numbers?
Temperature.
whatever we're, temperature.
That the temperature will be between 83.9 and 86 degrees. So, you could be asked on an exam to explain. That would be an explanation, right? Is not only get me these numbers, but tell me what these numbers mean. So how do you guys feel about confidence intervals? So those of you who came to the first review, I told you guys to become best friends with your formula sheet, right? Do that again for this exam. When you're working on this review, or when you're working on Samblum's review off of Canvas, have the formula sheet next to you. You can use that on the exam, so it's not cheating, it's not hindering you at all from the learning process. Have this formula sheet next to you, and when you write down all of the pieces of information, look at your formula sheet and see, okay, where does stuff start to fill in? Where am I looking to then plug these numbers in and get my answer? All right, so we have a couple more problems here where we're just looking up z-scores and t-scores. So I believe in class and on your homework, it's a lot of 90% confidence, 95%, 99% on your exam. I think she's probably already told you that that's not happening, right? She's going to throw weird confidence levels at you because some of you might have already memorized this 1.96, the 1.645, right? So those z-scores, you're gonna have to use different ones come exam day. So, if we're looking up the z-score for 90% confidence, what's our alpha?
10.
10%, right? 0.1. So alpha divided by 2, 0.05. And when we look up 0.05 in our z table, what do we find? So it's between 2, right?
Yeah.
So what do we need to do when it's between 2 like that? Take the average of the z-scores. So it's between 1.64 and 1.65. So that's why we average it out, and that z-score is 1.645. So why do we average that one, but we don't average it all the time? when it's between two different z-scores.
They're equal distance.
They're equal distance, right? So like when we did that top 9%, we picked the one that was closer. We didn't average them because the other z-score wasn't just as close. So when they're equal distance away, that's when we average up the z-scores, and that's the z that we'll be using. How about 82% confidence? What is alpha under 82% confidence?
18.
0.18, so 0.18 divided by 2, 0.09. And when we look up 0.09 in our z table, what do we find? What was that? Okay, is it closer to 1? Okay. So the z-score that we're going to use, 1.34. How about if we had 77% confidence? What is our alpha under 77% confidence? 0.23. So when we divide that by 2, what do we get?
1.5.
Okay. And when we look up that in our z table,
1.20.
what was it?
1.20.
1.20. So, you can always just test yourself with those while you're studying as well, right? Just come up with random confidence levels and then look up the z-scores. So, if we cannot use a z-score, if none of our proofs work out, what do we do?
T-score.
T-score, right? So if we have to use a t-score, then we're looking at a different table in our booklet. And what do we need in that table?